Now last time, what did we talk about? We talked about the comparison test, which really says, hey, let's look at two different series, and we'll say, well, let's look at how one compares versus the other compares, and then we can make a decision. But that means you have to compare two different things. And so now, today, we're going to talk about two different tests, which really says, let's look at ourselves, and we're going to compare our own sequence with itself and make some conclusions. Now, when we talk about comparing things with itself, what we're really going to get at, the important thing, is how fast we're going to call it the rate of growth. And when we talk about convergence or divergence, it oftentimes boils down to the question, how quickly do we go to zero? Do we go to zero fast enough, or do we go to zero too slowly? If we don't go to zero fast enough, then the terms have enough chance to accumulate and spin off to infinity. So the first test is called the ratio test. And we're going to suppose that all our terms are positive. And what we're going to look at is say, let's compare consecutive terms. So the next term over the current term. And suppose that converges. Okay, so we're looking at the limit as n goes to infinity of an plus 1 over an. Now, if it converges and that number is small in the sense that it's less than 1, then the sum will converge. If the number it goes to is large, it's bigger than 1, then the sum will diverge. And if the number equals 1, use a different test. All right, so that's actually not such a bad thing. Now what's going on here? Well, essentially what's going on is we're looking at what's happening to two consecutive terms. So, what's true? And there's the two cases. If our row is small, then there's just a little bit of space between 1 and row, because that's one of the nice things about the real numbers. So if I have my numbers here, if this is 1, then even if row is below 1, there's space here. So I can choose a little bit of a buffer, a row plus epsilon. And what happens is that eventually, because we say that the limit is row, eventually everything has to get close to row, so everything has to be nearby row. So what's the important thing? Well, the important thing is that if I look at the ratios, an plus 1 over an, that being bounded means that the next term is less than the current term times a number, rho plus epsilon. And that rho plus epsilon is a small number. And so, well, what does that say? Well, it says, really, you just repeat. So it's like every time you go down by a factor, at least as rho plus epsilon are bigger. So that says eventually everything, you can bound it by something like a sub n times rho plus epsilon to the k. Well, what is that? Well, that says, hey, look at the tail. And remember, the tail, that's going to tell the tale about convergence. So the tail here, that's going to behave in a geometric sense. Now, it's not exactly geometric, but it's bounded by something geometric. And so we can run a comparison test and say, hey, since the end of the series, the part that's the hard part, is going to be bounded by something geometric, and therefore the sum is going to converge. Okay. Now, row greater than 1, same idea. It just says, hey, now number line here is 1, here's row, and now we say, look, there's a lot of space in here, so I can find this number in between, row minus a little tiny piece. So what I get, same idea, is like every time I'm multiplying, at least in the tail, far down, every time I'm multiplying by something at least as big as rho minus epsilon, which means I'm multiplying by something which is causing things to get bigger and bigger and bigger. And so the terms are going to get huge. And so lo and behold, there's a geometric series and it's going to diverge. And so it's, again, going to be something which diverges. In fact, you can show now that if this is true, what will actually happen is that if you use the nth term test, it will show you, if you're very patient, that a sub n is going off to a huge number. So this will actually diverge by the nth term test. Now you might say, well, why don't we just use the nth term test? Well, because sometimes these limits are really hard to figure out what a sub n is doing, whereas the ratio can be very straightforward to work with. And we'll talk about some examples. All right, so now we have a plan. We're going to look at the ratios of the next term over the current term, ask what happens to that in the long run, and lo and behold, life will be good. Well, that's the plan. Let's talk about it. First thing to note, remember we said rho equals 1 is indecisive. Now, why is that? Well, the thing is, when rho equals 1, you don't have any space. You see, because the problem is, if this is 1 and it's rho, there's no wiggle room available. And since there's no wiggle room, you're out of hope. It's hopeless. All right, so let's use the ratio test. Now, look at these two series. Before we do the ratio test, what do we know about these series? Well, they're both p series. And so since we know about p series, this one is going to diverge, because I can think of it as n to the 1/2, and this one is going to converge, because it's n squared downstairs. Now, here we go. So, suppose that an is 1 over root n. Then, we take a look at the limit as n goes to infinity of an plus 1 over an. So that's the limit as n goes to infinity of 1 over square root of n plus 1 times a sub n. I'll just flip it over, root n over 1. Okay? So that's the limit as n goes to infinity of square root n over n plus 1. Well, it's not so hard to convince ourselves. N over n plus 1, you could, for example, multiply by 1 over n by 1 over n on the inside, but we can see that this limit is 1. All right, so here's an example where the ratio goes to 1, and it's a diverging sum. And now, if we do the other one, well, we can kind of predict what's going to happen, but we'll do it, right? Because we need the practice, 1 over n squared. So that's the limit, n goes to infinity. Again, look at consecutive terms, an plus 1 over an. All right, well, that becomes the limit, n goes to infinity, of 1 over n plus 1 squared times, flip it over, n squared over 1. So, this is the limit, as n goes to infinity, of n squared, and downstairs it's really n squared plus 2n plus 1. Now you could do lots of things. You could do the L'Hopital, you could just say multiply top and bottom by 1 over n squared. But in general, when you have a polynomial over a polynomial, and the leading powers are the same, so this is both degree 2, then you get the leading coefficients are what's going to be the limit. And so this is 1. So again, here's a case where the ratio goes to 1, but it converges. And that's why we say rho equals 1. It's indecisive, because either thing can happen. It could converge or it could diverge. And so you want to be careful. You want to be the right amount of careful. All right. So the next question. Does the sum from 1 to infinity of n factorial divided by 2 to the power of n squared converge? All right. Now, you might think, well, we said n factorial is really, really fast, and that's 2 to n squared. Isn't that exponential? And, well, be careful. 2 to the n is exponential. That's 2 to the n squared. That's even bigger. And so it's not so clear. Which is growing faster, n factorial or 2 to the n squared? And which one is growing faster fast enough? If we ask the question, what's the limit as n goes to infinity of n factorial over 2 to the n squared, we'd have a hard time answering this question with our current tools. What's our problems? Well, our problem is we don't have a great way to say, n factorial. We'd like to say, all right, goes to infinity, sure, but we can't apply L'Hopital because we can't take a derivative of it. At least not of it in its current form. There are ways to do that, but that's for a different kind of class. And so the nth term test is hard for us to do. But maybe we can make some progress with our new test, right? I mean, we've got a shiny new toy. We should use it. So let's pull out our new toy. So we're going to apply the ratio test. And all right, good. And we'll talk about why ratio test is good for this in just a second. So what do we have? Well, we're going to take a limit as n goes to infinity of an plus 1 divided by an, where this expression right here, this is our a sub n. Now, how do we get an plus 1? We should actually pause for a second, and this is one of the places where people sometimes get tripped up. It's like, okay, I know what an is. I can just copy it down. What does it mean to get an plus 1? Well, what you should think of is if I want a sub n plus 1, what I'll do is everywhere where I see an n, I'm going to put an n plus 1. And this is a nice reminder that when you're doing things like this, parentheses are your friend. Now, you're probably thinking, wow, I have a lot of friends. 0's my friend, 1's my friend, parentheses my friend. Absolutely. You have many friends trying to work with you to help you succeed. So make sure you take advantage of them. So, here we go. To find an plus 1, I'm going to come into this expression, and everywhere where I see an n, I'm going to put an n plus 1. So, parenthesis, n plus 1 factorial, divide that by 2 to the n plus 1 squared. Okay? You see what we did there? Everywhere we saw an n, we replaced it by n plus 1. And we were very generous with our parentheses. Now, how about an? Well, we're just copying it. And because we divide by n, we can multiply by the reciprocal. So that's 2 to the n squared. Divide that by n factorial. Now, our goal is to simplify. And it's a worthy goal, right? Okay, so how can we simplify? Well, first off, let's talk about the factorials. We should do a little bit of divergence here. So, if we rewrite this, this is the limit as n heads off to infinity of n plus 1 factorial over n factorial times 2 to the power n squared. Divide that, and I'll say 2 to the power, and I can multiply that out, n squared plus 2n plus 1. All right? So that's what we have. Now, we got to deal with both these pieces. So let's talk about n plus 1 factorial over n factorial. Now, here's the thing about factorials. If I think about n plus 1 factorial, that's really n plus 1 times n minus 1 times n minus 2, and so forth and so on, down to the n. But the key here to observe is this last part is n factorial. So I can write this as n plus 1 times n factorial. Now what that's saying is if I have a factorial here, I can pull off the first term, and then I'll be left with a slightly smaller factorial. In fact, I can pull off however many terms I need. So that's how we'll deal with the first piece. All right, so we get the limit as n goes to infinity. Now I only need to pull off one term because I just need to pull off enough to help me get cancellation. Okay, and now, lo and behold, once I have enough for cancellation, life is good. How about the exponents? Well, that's not so hard either. What do? Well, you just take a subtraction. So you can take the top minus the bottom, or you can take the bottom minus the top, just leave it downstairs. So I'm going to do, since it seems like the bottom is bigger here, in fact, well, there's a couple things. Here's one thing we can do. If we don't like to think of it as subtraction, I can think of it as 2 to the n squared. Downstairs I have 2 to the n squared plus 2, sorry, not plus, times 2 to the 2n times 2 to the 1, right? Because addition becomes multiplication, and again, lo and behold, I can cancel. So, what's left? Well, I have the limit as n goes to infinity. Upstairs I have n plus 1. Downstairs I have 2 to the 2n, which is same as 4 to the n, because it's really 2 squared to the n, and then there's a 2. So, now we're to the place where we say, what's going on? If we stare at this, and we don't have to stare very long, I mean, we should understand these things. The top, what is it growing like? Well, it's a polynomial. It's n. The bottom, what is that growing like? It's exponential. And now, which wins between polynomial and exponential? The answer is that exponential wins every time. That's an amazing thing about exponential growth. It just zooms off. So the limit is 0. All right, so what does that say? Well, we've applied the ratio test, and that says if the ratio test is small, in particular, it's less than 1, and it's definitely true that 0 is less than 1, then what we can conclude is that this is going to converge. So the sum n equals 1 to infinity, n factorial over 2 to the n squared converges by our ratio test. All right, so there's our answer, which, by the way, tells us that now, since we know it converges, it has to be the case that this limit is 0, which tells us that, look, even though factorial grows fast, there's something that grows faster. Because yes, no matter how big you are, there's always a bigger thing. And so, well, that's good to know. Now, when do we use the ratio test? Because, there's lots of tests. We want to know, when is this test used? When is that test used? And so, when is the ratio test used? And I'll tell you that there's sort of one big clue that if you see something, you should use the ratio test. And that is, if you see factorials, it's great for the ratio test. And the reason that the factorials are great for the ratio test are what we just talked about. It's the fact that we can start to pull off terms from the factorials. All right. So here's this question. Does n factorial times 4n factorial divide that by 2n factorial times 3n factorial, does that converge? Or does it not converge? All right. Well, let's figure this out. Okay, so we're going to use our ratio test. So this is our a sub n. All right, and I see that we've left ourselves a lot of real estate, so it makes me a little bit nervous about what's coming, but we start, and let's see where it takes us. Okay, so idea is let's apply our ratio test. So we're going to take a look at the limit as n goes to infinity of a sub n plus 1 over a sub n. Now, remember, the first thing we have to do is figure out what is a sub n plus 1. And that is everywhere that you see an n, And so there's a couple of different places where n shows up. We're going to put in n plus 1. And remember, be generous with your parentheses, because we want to make sure we get the right expression. So we'll just go through it term by term. So n factorial will become n plus 1 factorial. How about 4n factorial? Well, it's going to be 4, and then I'm going to replace the n by n plus 1 factorial. Now, why did we need the parenthesis here? Because it's 4 times n plus 1, which means that when we distribute this through, in other words, this being the 4, what's going to happen is it's really going to be 4n plus 4. So you want to be careful, because here's where you can make a mistake. 4n plus 4 factorial is very different from 4n factorial. All right, how about downstairs? Well, 2 times n plus 1 factorial and 3 times n plus 1 factorial. Right? Okay, that's the a sub n plus 1. Multiply that by the reciprocal of a sub n. See how we're dividing by a sub n? That's the same as multiplying by the reciprocal. So that's 2n factorial, 3n factorial, divide that by n factorial, and 4n factorial. Now what we can do is we can actually group things. So for instance, let's see, this term n plus 1 factorial matches nicely with the n factorial. The 4n plus 1 factorial matches nicely with the 4n factorial. So 4 times n plus 1 factorial over 4n factorial. And let's see, the 2n factorial matches nicely with this 2 times n plus 1 factorial. So 2n factorial, and then 2 times n plus 1 factorial. And the 3n factorial matches nicely with the 3 times n plus 1 factorial. All right? There we go. Got them all, right? Right. Good. Good, good, good. Now, here's the next thing, is we're going to remember that we can pull terms off. So, let's think about this. Now, we'll just make a couple notes here. This is really 4n plus 4. And this is really 2n plus 2. And this is really 3n plus 3. So that's for our reference. Okay, so here we go. Now, the n plus 1 factorial versus n factorial. So what I want to do is I want to pull enough off of the top term so it cancels with the bottom term. So I start. Well, I get n plus 1, and then I have n factorial left over, which is just right. So that's the first term. Okay, now the next term, this is the one, I have 4n plus 4 factorial. Now what is that? Well, 4n plus 4, if I pull off the first term, it's 4n plus 4. The next term, 4n plus 3. The next term, 4n plus 2. The next term is 4n plus 1. And then the next term is 4n. And then I say, oh wait, once I start here, it's going to be 4n factorial for the rest. So that's 4n factorial. So what I did there is I pulled off the first 4 terms. See how there's plus 4? That means I really need to pull off the first 4 terms so I get my cancellation. So the next term, that'll be 2n factorial, and it's the downstairs I'm going to pull off now. So 2n plus 2, 2n plus 1, and then the rest of it, whoops, is 2n factorial after that point. And then the last term, 3n factorial, and then we're going to pull off terms downstairs. 3n plus 3, 3n plus 2, 3n plus 1, and 3n factorial. All right. Okay, good. Now this is why the ratio test works so well, is because you can pull off terms and then you get cancellation. That's why we like the ratio test for things which involve factorials. So we can cancel the n factorials, the 4n factorials, the 2n factorials, and the 3n factorials. Now what's left? Well, what's left, if you look, it's just polynomials. And it's a lot of polynomials. So now we have a sort of like, what are we going to do? Well, let's figure out the degree of the polynomial. So we have 1, 2, 3, 4, 5 terms upstairs, 1, 2, 3, 4, 5 terms downstairs. So it's a fifth degree polynomial over a fifth degree polynomial. Well, that's good. So we've got to figure out what the limit is. Now, one way to do it is to say, let's do the following. Let's slow it down. So I'm going to multiply top and bottom by 1 over n to the fifth. Now, why 1 over n to the fifth? Well, I said it was a fifth degree polynomial. So if I multiply by 1 over n to the fifth, that's just enough that it's going to slow things down. So I'm going to think of multiplying every single term. There's 5 terms by 1 over n. So that's what we're doing. So this is the limit as n goes to infinity of, in the first term, it would be 1 plus 1 over n. The second term, 4 plus 4 over n. Then 4 plus 3 over n. And 4 plus 2 over n. And then 4 plus 1 over n. Downstairs, we're going to get 2 plus 2 over n. And then we're going to get 2 plus 1 over n. And then we're going to get 3 plus 3 over n. 3 plus 2 over n. And 3 plus 1 over n. Okay? So I took each one of the 5 terms and I divided it by n. Because there were 5 terms on top and 5 terms on the bottom, that's the same. And now we say, this is easy. Because all the terms that involve n are going to go to 0. So this is going to be 1 times 4 times 4 times 4 times 4. Divide that by 2 times 2 times 3 times 3 times 3. Well, if I take 4 times 4 times 4 times 4, what do we get? Well, that's a lot of 4s. It's very 4-y. It's 256. Downstairs, I get 2 times 2, which is 4. 3 times 3 times 3 is 27. So that's 256. Divide that by 4 times 27 is 108. Now, you could simplify, but what are we after? What we're after is the size of this number in relationship to 1. Is it smaller than 1? Is it bigger than 1? Well, that's clearly a lot bigger than 1. In fact, it's bigger than 2. So the ratio is bigger than 1, which means that as you get further and further down, it's getting larger and larger and larger. And so large, well, it's not going to converge. So does it converge? No. That's the answer. By the ratio test. Because the ratio test, the limit goes to something which is bigger than 1. So in some sense, that 4n factorial, really hard to recover from that. Now, of course, there's lots of variations of this. And on a side note, I suspect we'll have this coming up at some point in the near future. But it's good to mention it now, because you might see this. What happens if you have, say, n to the n, and you were to do the ratio test? Let's say you have n to the n, divide that by n factorial, right? And you want to know, does this converge or does this diverge? Well, let's suppose that this was our a sub n, and so this is just a little side note here. If we take the limit as n goes to infinity of a sub n plus 1 over a sub n, well, that's n plus 1 to the power n plus 1, and then we're going to divide that by n plus 1 factorial, times it by the reciprocal n factorial, and n to the n. Now what can you do? Whoop, we're still not a limit here. Ha ha ha. Don't forget, notation. Notation is important. Notation is important. Now, if we do the same trick, what's the same trick? And I don't want to make it sound like it's just full of tricks. Same technique. Yeah, there we go. Same technique. Pull off enough so that what's left can cancel. So you can cancel an n factorial. Now notice, what do you have? You have an n plus 1. Here's a bunch of n plus 1s. So this becomes the limit as n goes to infinity of n plus 1 to the power n divided by n to the power n, which is the limit as n goes to infinity of 1 plus 1 over n to the nth power. Now, what does that do? This is an important limit because it shows up, because if you do things like the ratio test, this type of limit shows up. We've actually seen this before, and I promise you, I'm not making that statement up. We really, really, really have seen this before. Do you remember it? Do you remember it? It's a lot of fun. It's E. Now, in case you're wondering, what? So, we did this back just last week. So, in general, here's the useful fact to remember, and this really is something that's good to remember. Limit as n goes to infinity of, say, 1 plus t over n to the nth power is equal to e to the t. And that's true for any choice of t. And so in this case, t equals 1, you get e. And so it's not so unusual to see, if you have expressions which have things like n to the n showing up, that you get this expression that seems to involve e as well. And actually that's not so surprising. It does turn out that one of the ways you can approximate n factorial does involve the constant e. So it's not such an outlandish thing. Okay, so anyways, that's the ratio test. But there's a second test. And the second test is called the root test. So ratio and root. And how does the root test work? Well, it says, suppose you have a sequence, positive sequence of numbers, and you have the limit as n goes to infinity, the nth root. See, that's how you know how the root test works, is you're taking the root of it. Whereas the ratio, you were taking a ratio of things. All right, well, suppose that limit exists. Well, if that limit is small, then the sum definitely is going to converge. If that limit is large, then the sum will definitely diverge, where small and large says relative to 1. Are you below 1? Are you above 1? And if you're equal to 1, forget it. Use a different test. Now, if you look at the ratio test and the root test, they both are very similar. You're both computing limits, and you're both looking at things, are you below 1 or are you above 1? All right, so how do you decide? Now, there's sort of the statement here, where do you look for clues? And so here are some clues. If everything you see is raised to a power, or most things are raised to a power, use a root test. If there are factorials, consider a ratio test. The word consider is really almost too weak. Must use. Because there's almost no other choice. And of course, when in doubt, try both. I think that there's a tendency for people to use the root test more often, and I think that's perfectly fine. Now, why do we use it? Well, if you think about what's happening here, what we have is, lo and behold, if the limit as n goes to infinity of a sub n to the 1 over n is rho, what you really have is that a sub n to the 1 over n is about rho. Because if you take the limit, then lo and behold, then you're about what you approach. So that says a sub n is about rho to the n. And so kind of the idea with the root test, it's actually similar to the ratio test, is it's trying to behave like a geometric sequence. And now you do the same thing that you did before. To make it precise, you say, well, look, if your limit is below 1, then eventually, if you go far enough out, you're less than some rho plus a little tiny bit. You get a little bit of wiggle room. So a sub n is less than rho plus epsilon to the n. And now that thing, because it's smaller than 1, it's got to converge. And life is good. And if you're above 1, again, you get a little bit of wiggle room. You can say, hey, rho minus epsilon is above 1, which means that the terms, they're getting big. And they're going to blow up. And in fact, what happens if rho is greater than 1, then the nth term test kicks in, and it says, hey, these terms get huge. So it's going to be the case that this is a sub n goes off to infinity. Again, if rho equals 1, you're out of luck. No hope. No hope at all. All right. Well, let's try some examples. Okay. Does 1.001 to the n, divide that by n to the 1,000. Does it converge? Yes or no? Now looking at this, you might say, okay, well let's just think about the first few cases. If I plug in n equals 1, you get 1.001, that's pretty small, and you get downstairs 1. Okay, so it's about 1. If you plug in n equals 2, upstairs 1.001 squared is actually pretty small. It's like 1.002 maybe, give or take. On the other hand, 2 to the 1,000 is huge. It's a gigantic number. And so when you plug in n equals 2, you're going to get 0.0000, a couple hundred zeros. 1. You know, that's tiny. N equals 3, unimaginably small. And indeed, if you go through the first billion terms, the numbers are super, super tiny. If you first go through the first trillion terms, again, very, very small numbers are going to show up. So if you were just to go by the first, few billion, few trillion terms, you'd say all these numbers are very small, and if you add them up, they're basically insignificant. I mean, the calculator can't even register these numbers. So does that mean it converges? Well, no, because you've got to be careful, because the story about convergence, I've said this before, but it's a good thing to remind ourselves of. Convergence always happens towards the end. What happens in the long run? All right, so, well, let's use our nth root test, right? Our root test. That's what we just learned. So this is our a sub n. So what we're after here is we're going to take our limit as n goes to infinity of a sub n to the power 1 over n. Now, one thing that's suggesting we should try to do the root test is the fact that we see this to the nth power. So whenever we see something to the nth power, that's a clue. Use the root test. So this will be the limit as n tends to infinity of, well, 1.001 to the n over n to the 1,000, and that's going to be to the 1 over nth power. So that's going to be the limit. N goes to infinity. If I take 1.001 to the n, then I raise it to the power 1 over n. Well, power to power, what do you do with those exponents? You multiply them together. So that's 1.001 to the power 1. Well, that can be simplified. And then downstairs you have n to the 1,000 to the 1 over n. Now, let's talk about things we can do. Well, first off, we'll just simplify the top just to say it's 1.001. Now, downstairs, do you see how we have n to the 1,000 to the 1 over n? We can swap. And by that, I mean we can write this as n to the 1 over n and raise it to the 1,000th power. What does this go to? Well, again, let's just have a little bit of a side comment here. What's the limit as n goes to infinity, n to the 1 over n power? Now, This is also one we talked about a week ago, and I claim we know the answer to this. Do you remember it? It's kind of fun. It's the number 1. So if you have the nth root of n, that goes to 1 as n goes to infinity, which says that this piece right here, which is the only place where n shows up, that's going to 1. So our limit then is the following. It's 1.001 over 1 to the 1000th power. Well, if you take 1 to the 1000, it's still 1. So it's 1.001. Now, how does 1.001 compare to the number 1? Well, it's bigger than 1. See, it's 0.001 bigger than 1. So it's really close to 1, but it doesn't matter that it's close to 1. It matters that it's bigger than 1. And so what's the conclusion? Well, by the root test, that's the problem with the root and the ratio test. They're too similar in the way they're written and they sound. So since a sub n to the 1 over n goes to rho, which is 1.001, which is bigger than 1, then by the root test, what's our conclusion? The series diverges. And this just shows you the power of exponential. Because initially you look at that and say that the top is growing very, very slowly. Very, very slow. And the bottom, it starts off, it's really growing quite quickly. And the bottom will grow quite quick, even if we're very patient. But in the long run, if we're patient, we'll see that, lo and behold, that things will diverge. Exponential will always beat polynomial. All right, let's do another question. The sum, n equals 1 to infinity, of 1 minus 3 over n to the nth power. Does this converge or diverge? All right. Well, let's see. We see, lo and behold, there's an n there, right? Okay, good. Now, so that says, hey, let's apply the root test. And since we just learned it, that's very tempting, so let's go ahead and do it. So we're going to take the limit as n goes to infinity of, we take our term 1 minus 3 over n to the nth power to the 1 over n. So that's the limit as n goes to infinity of 1 minus 3 over n, right? Because if I take something to the nth power, then take the nth root, that's the same as just taking the something. And what's this limit? Well, there's only one single n, and as we go off to infinity, that's going to get small, that expression on the end. So this is going to go to 1. All right, now, that says right now, our limit is 1. So, when our limit is 1 in the root test, what's our conclusion? The conclusion is we need to do more work. So, inconclusive. Because this is the same thing we saw before. It's possible for the limit to be 1 and have something which converges, and it's possible to have the limit be 1 and be something which diverges. All right, so let's apply a different test. Now, let's just look at the following. Well, let's look at the limit as n goes to infinity of a sub n. Because this actually looks really familiar. We talked about this kind of thing just a few minutes ago. That's the limit as n goes to infinity of 1 minus 3 over n to the n. Now let's see if you remember what we said this was. Do you remember what it is? Another way we could write this, if it helps, that's the limit n goes to infinity of 1 plus negative 3 over n to the nth power. And that is e to the minus 3. So we mentioned a couple of slides back. Let's see if we can find that slide again. Yeah, here it is. See? If I take, there it is. 1 plus t over n to the nth power, it's e to the t. Well, this is that expression where t is negative 3. All right, cool. Now, here's the cool thing about e to the negative 3. E to the negative 3, it's less than 1, right? And you're probably thinking, cool, less than 1, that's going to be convergent, right? And be careful. Be really careful. Here's something that frequently happens. The fact that this is less than 1, this is not important for this test. Now, you might say, wait, what test are we in? Well, we're looking at the limit of just an. So when you see this expression, limit as n goes to infinity of an, that is not the root test, and it's not the ratio test. This is the nth term test. And so you want to make sure you understand which test you're in, because you don't want to start mixing them together. So when we have a test and we're saying, well, the limit is less than 1 and the limit is above 1, that's only going to show up in the ratio test or the root test. In the other limits, we have the question of, is the limit 0? Is it any number? Is it infinity? So the fact that it's smaller than 1 doesn't matter. In the nth term test, what do we care about? Well, the question is, where does it go to? And this answer is e to the negative 3. The real important thing is that e to the negative 3 is not 0. So that says in the limit, as n goes to infinity, the terms are not going to 0. So what's the conclusion? Well, the conclusion is that if the terms don't go to 0, this has to diverge. All right, so be careful. And I do know that as we go further along, there start to be lots and lots of tests, and it can be really confusing to keep them straight. But that's why we practice. And the more we practice, the better that we get. Okay, one last example for now. Let a sub n be defined in the following way. A sub n is n over 2 to the n if n is even, and it's 1 over 2 to the n if n is odd. And it says apply both the ratio test and the root test to determine whether the sum of a sub n converges. Now, what does this look like? Well, if you write down the first couple of terms, so n equals 1 would be this bottom expression. So you get 1 over 2. N equals 2. Well, that's going to be the top expression, 2 over 2 squared. N equals 3, 1 over 2 cubed. N equals 4, 4 over 2 to the 4th. N equals 5, 1 over 2 to the 5th. N equals 6, 6 over 2 to the 6th. N equals 7, 1 over 2 to the 7th. And so forth and so on. Now, what do you see? Well, what you see is that there's a lot of numbers here. What are we trying to get at? Okay. So suppose we were applying the ratio test. And so the ratio test says, let's look at an plus 1 over an. Now, be careful here. Let's be really, really careful. Let's suppose for a second here that n is even. So that says that a sub n, if n is even, then the denominator looks like n divided by 2 to the n, and then the numerator will be n plus 1. If n is even, n plus 1 is odd, so it looks like 1 over 2 to the n plus 1. Now, if you take a look at this ratio here, you can get some cancellation with the 2 to the n's. The n stays downstairs. There's an extra 2 left over because of that plus 1. So that's 1 over 2 times n. That's if n is even. So, what if n is odd? Okay? If n is odd, now the denominator looks like 1 over 2 to the n. And the numerator, if n is odd, n plus 1 is even. So that looks like n plus 1, divide that by 2 to the power n plus 1. And if you clean this up, you can get again some cancellations with 2 to the n. So that's n plus 1 over 2. Now what's the question here? Well, what happens to the limit as n goes to infinity of a n plus 1 over a n? Well, it really depends whether you look at the evens or the odds. If you're only looking at the evens, the numbers are getting smaller and smaller. If you only look at the odds, the numbers are getting bigger and bigger. So what happens is it's sort of like small, big, small, big, small, big, small, big, small, big, small, big. What's the limit? Well, the limit, it doesn't exist because it can't make up its mind. Half the time it thinks it should be 0, half the time it thinks it should be huge, and so it cannot decide what it should be. And so the ratio test, that says, look, the ratio test, no conclusion. Can't make up its mind. All right. Now, that's the ratio test. Let's flip, because we said apply both. So, what's the other test? The other test is the root test. So, that's going to be a sub n to the 1 over n. So again, let's be careful. We're going to do two cases. N is even, n is odd. Now, if n is even, all right, so then we have n over 2 to the n, to the 1 over n power, which is n to the 1 over n over 2. Because I can take up both the numerator and the denominator to the 1 over nth power. On the other hand, if n is odd, it's 1 over 2 to the n to the 1 over n. Well, that's the same as 1 to the 1 over n, which is 1, and 2 to the n to the 1 over n, which is 2. So that's 1 over 2. So, what's the limit as n goes to infinity of a n to the 1 over n? Well, if I'm odd, I think I'm always a half. What happens if I'm even? Well, what happens to n to the 1 over n? It's going to get close to 1. So, n to the 1 over n over 2 gets close to a half. So it doesn't matter, even or odd, I still think I'm approaching a half. Now, what's true about a half? A half is less than 1. And so, the root test says what? Well, the limit of the root, the nth root of a sub n, is something that's smaller than 1, so that says it converges. So in some sense, this shows you that the root test can answer questions that the ratio test can't. And generally speaking, the root test is probably a little bit more powerful. Now, there were other tests that we could have used. We could have done something very simple. For example, we could have done a comparison test, because we actually know how to find the value of the sum of n over 2 to the n. But, well, that's a different story. But anyways, we know that we have 2 new tests, which is pretty good. We're almost near the end of our test. We're going to learn 1 or 2 more. Got to keep going, right? There's always more to learn. That's the great thing. There's always something new. But that's it for today, and we'll pick up again next time. See you later. Bye.